Hello, so in this video we're going to be talking about this idea of linearisation, about some equilibrium point. Okay, now it kind of sounds, some of it perhaps will sound familiar. Well, we've met equilibrium point before, okay, because that's just like a stationary point. Okay, so we're happy with equilibrium point, and linearisation is exactly that. So basically we're turning something that may not be linear into something that basically is linear. Okay, and if you remember, we had this ODE. This is kind of a standard first order ODE, which basically involves the derivative, so the derivative of y with respect to t. So we're assuming that y is a function of t. Okay, that's kind of the y function that we're considering in this ODE. So we got the derivative of y, and we've also got that is equal to some function involving y. Now at the moment, this right hand side is just a function, and we're told it's just a function involving y. Well, it may be linear or it may not be linear. Okay, so what we want to basically do is try and basically make this right hand side. We assume it's not linear. We want to basically perform a function, an operation, I suppose, that makes this right hand side linear. Okay, and that's essentially what we're doing in this video. Okay, because it just makes things easier to deal with, right? Okay, so remember what we can get out of this. So if we set this equal to 0, so if we set this thing equal to 0, we'll get the equilibrium point out. Okay, we'll get an equilibrium point out. So we're going to call that equilibrium point YE. Okay, it's going to be the equilibrium point of Y, so we're going to call it Y, little subscript E. All right. And notice that if we set, what we're doing is we're basically setting dy by dt equals 0. That's kind of standard. That's how you find a stationary point, right? You set the derivative equal to 0 because that's where the gradient is equal to 0. So that's exactly what you're doing here, and you get the equilibrium point out. Well, look, we've set dy by dt equal to 0, but look what dy by dt is equal to. It's equal to f of y, right? So therefore, because we've set dy by dt equal to 0, then at an equilibrium point, so y equals, if you like, ye, yeah, that's our equilibrium point, which we're getting out from dy by dt. Well, we've set dy by dt equal to 0. Well, because dy by dt is equal to f of y, right, then at the equilibrium point, so at the equilibrium point ye, okay, then the function must also be equal to 0. Are you happy with that? Yeah, because we've set dy by dt equal to 0 to get the equilibrium point, all right? And we know that dy by dt is equal to the function. Okay, so in other words, when we put that particular point into our function, okay, then that should be equal to 0 because dy by dt is equal to 0 at the equilibrium point. Yeah? Okay, so hopefully that makes a bit of sense. If not, go away and think about it. So in other words, what we've got is we've got f of ye equals 0. Sorry, I shouldn't have rubbed that out. F of ye equals 0, effectively. Okay, so the idea is okay, we want to basically try and we want to look at this point ye now. So imagine I'm just going to draw it on my y-axis. So this is just my y-axis now. Okay, and I'm going to plot my point ye on my axis, on my line. Sorry, so this is ye on my line. Okay, then the idea is that I want to move some really small distance away from this point ye. So in other words, I want to move some really small distance away from ye, and it's a really small distance, but obviously if I draw it really small, you're not going to be able to see it, so I'm going to scale it up a bit. But this distance here, this distance which I've drawn in here, is really small, and this new point which I'm going to move to is just going to be some general point. Okay, so I'm just going to call it y. It's just going to be some general point that I move to. But the point is that I've moved some really small distance, and that really small distance I'm going to call y tilde. Sorry, that's bad tilde. So it's a bit like a little wavy line above the y. And I'm going to call that y tilde. Okay, so that is a really small distance I move away from ye, and I get to some general point y, effectively. So now I can write an equation for that. So basically, y, my new point y, is equal to, well, what's it equal to? It's equal to ye, my point that I was at, plus my really small distance y tilde. Okay, so this is my new point y. Basically, I've moved a really small distance away from ye. Okay, it could be to the right, it could be to the left. It's just some really small distance. I'm just going to consider for the moment that we're moving, to the right. Okay, so hopefully you're up to that by now. Now, I'm going to come back now to my Taylor series, okay, which I have spoken about before in other videos. Okay, so I've done a couple of videos, I think, on Taylor series, and I'm going to come back to that. So remember what my Taylor series is. I'm just going to write it out now. It's going to be f of x So my function could be approximated by effectively a power series, a special type of power series. And it is my function evaluated at my point A. So I'm considering my function about some point A. Okay, so the expansion of my function around some point A is equal to f of A plus, where are we? Oops, my pen's not working. There we go. Plus f dash of A times x minus A. Yep. Plus f double dash of A over 2 factorial times x minus A squared, plus, and we can carry on going, and we can keep going like that, effectively. All right. Now what I'm going to do is I'm going to consider, basically, my point, at the moment, this is around my point A. This is around my point A. So in other words, around my point x equals A. So around my point x equals A. What I'm now going to do is I'm going to consider my function expanded around a point which is really, really close to A. So I'm going to consider my function expanded around another point, but a point which is really, really close to A, and I'm going to call that point A plus H. So in other words, before I was considering my function around, this is my x-axis, I was considering my expansion of my function, around my point A, What I'm now going to do is I'm going to move some point really, really close to A, okay, and I'm going to call that point A plus H. So in other words, I'm going to move by some distance H, and considering the expansion of my function around that now new point, that point A plus H. Okay, so right, so I can now use what I've written. Above with my Taylor series. Okay, this Taylor series up here, just by considering now. Well, my new point is x equals A plus H. So what is the Taylor series expansion around that new point? Well, it's basically, whenever I see an x, I'm going to replace it with A plus H. Okay, and whenever I see an A, well, look at this. Okay, if I now rearrange this to get H equals x minus A, okay, so now whenever I see an x minus A, so for example in there, whenever I see an x minus A, I'll just replace it with H, okay, and whenever I see an x minus A in there, so I'll just replace it with H effectively now. Alright, so in other words, when I now consider my expansion, so I'm considering my expansion around now my point A plus H, it's no longer x, so it's A plus H, I'm just literally replacing x equals A plus H, okay, that is equal to f of A still, okay. I could rearrange this, I suppose, to get A, but to be quite honest with you, I'm happy with using A at the moment. That's absolutely fine. I'm just going to leave that alone. F of A plus, what's it going to be? Plus f dash of A. Now my x minus A is no longer x minus A, it's now H. Okay, so it's now H, so this is just an H here, plus f double dash of A over 2 factorial. Again, x minus A here, so I'm just going to replace it with H, and of course it was x minus A squared, so now it's going to be H squared, and I can carry on going like that. So, okay, so now this is my new expansion around my new point over here, my new point A plus H. The expansion of my function around a new point x plus H. A plus H. Well, why have I done that? Because that's exactly the same situation as I've got going up here. I now want to consider, I can consider an expansion around my point, my function around my point ye, but I now want to consider the expansion of my point around a point which is really close to ye. It's actually it's y, okay, and I know that y equals ye plus h. So in other words, where I consider my expansion of my function equals x equals a plus h, right? The expansion of my function around x equals a plus h. Okay, I can now simply do a bit of replacing to find the expansion of my function around ye plus y tilde. So basically, this is exactly what I'm doing. I'm just now replacing variables. Okay, I've got all the pieces in my puzzle. I just need to kind of put them all together. Okay, so here, basically, so in other words, I'm saying that x equals y, okay, and that h equals ye, okay, and that h equals y tilde. Okay, so that's effectively what I now need to do. I need to replace that in here. So let me just write that out again. Okay, so here we've got it down here again. Okay, and so now I'll just want to consider the expansion around my point f of y. Okay, so around my new point f of y, which of course just up here this was a plus h. Yeah, so this new point this new point y, which of course was the equivalent of a plus h in my previous case. So what have we got? We've got that is equal to, well, f of a it was, so now a is equal to ye. So it's now f of ye plus f dash, not of a, of ye. Now just replaced a with ye, and where I had h before, I'm now going to replace that with x. Okay, so this is now x. Sorry, no. Sorry, no, what am I doing? This is, when I had h before, this is y tilde. Don't know why I said x. There we go, this is y tilde. Okay, this is y tilde plus f double dash of a. So it's no longer a, it's now ye. Okay, over 2 factorial times h, which was y tilde, all squared. And I can carry on going like that. So now this is my new expansion around my point. Where are we? Around this new point, y. Okay, so the expansion of my function around my new point y. So in other words, I'm considering a point which is really, really close to my equilibrium point. So I'm considering my function being expanded around a point which is really, really close to my equilibrium point. Okay, and this is the expansion of my function. This is the expansion of my function around that point which is really close to my equilibrium point. Okay, cool. So what can I do with this? What can I do with this? Well, because look where I am. Okay, if I just draw this out again. So we had ye. Okay, and then I moved by some distance, y tilde, so really, really small distance, to a new point, y. Okay, well, because y is really, really close to ye, if you remember with the Taylor expansion, okay, the more terms which you have in a Taylor expansion, the better the approximation of the function. So basically, you know, a few terms will only consider a small part of the function, more terms will basically consider more and more, you know, a wider and wider range of the function. Well, because I'm so close here, because I'm so close to my equilibrium point, I don't need that many terms. Okay, I only need a few terms. So say, for example, 2 terms will do absolutely fine because I'm only very, very close to my equilibrium point. Okay, so I've got my function here, something like that, and because I'm only considering a point which is really, really close to my equilibrium point, so, you know, I only need to consider a really, really small, you know, a few terms in my expansion. So I'm only actually going to consider the first 2 terms. So I'm only going to actually consider that part of the expansion. So I don't even need to consider anything after that point. Okay, so in other words, a good approximation of my function would just be a first couple of terms. This is f of ye plus f dash of ye times y tilde. Okay, and that is a good expansion, a good approximation for my expansion around my point f of y. Okay, for my function around my point y. Okay, now notice that f of ye, well, ye is just going to be a number. Okay, so when I take the function of my number, when I put a number into my function, that's still going to be a number. So that part there is just going to be some number. Okay, so just some number. Right. So in other words, I can say that f of y. So it's not. In other words, it's not going to actually make that much difference to my function. Okay, it's not going to make that much difference to my function. You know, say for example, if I had a function y equals x squared plus 2, for example, all right, having this 2 here isn't going to make a blind bit of difference to this shape of my function. It's going to make a blind difference because again, it's just an approximation, right? This is just an approximation. I should write an approximate equal there. This is just an approximation to my function. So just having this plus 2 here isn't going to make a big bit of difference to my function, you know, the overall shape of my function. Y equals x squared plus 2. You know, this plus 2 isn't going to make a bit of difference. So if I cross this off, you know, and it's an approximation anyway, so if I just get rid of that number there, it's not going to make a huge bit of difference. You know, I've still got the important part, which is the y equals x squared shape. Okay, so likewise, I can say that f of y can just be written approximately as y tilde. So in other words, I just ignore that number there, you know, because it's not going to make that much difference to my function. It's an approximation in the first place. Having that number there isn't going to make a huge bit of difference. Okay, and in actual fact, because you know it's such a small, you know, I'm considering such a small distance. I'm considering such a small distance y tilde. All right, you know, I'm actually just going to write this as an equals. Just purely because it's such a small difference. So actually, it's such a small section of the function that I'm considering anyway, that, you know, actually, do you know what? An approximately equal and an equal sign, it's going to be so similar because it's such a small section of the function. They're going to be so very, very similar anyway. I'm not really worried about approximately. Okay, it's a negligible difference. I'm just for convenience going to change this to an equals effectively. Okay. So in other words, this is what I end up with. Now, I want you to notice, okay, what we had before. We had y. What did we have before? We said that y was equal to my equilibrium point plus some really, really small distance y tilde. Okay. Now notice as well that we had that, or we can show as well that dy by dt, okay, so dy by dt is equal to, if I just replace this y, excuse me, this y with ye plus y tilde, so I end up with a derivative of ye plus y tilde. Well, this ye, like I've just said before, is just a number. It is just a number. It's an equilibrium point. It's just a number. Okay. You know, my y tilde won't be. Yeah. So ye will just be a number. Okay. So in other words, it can just be equal to 0. All right. So when I take the derivative, it will just be equal to 0. So what I end up with is dy tilde by dt. So the derivative of y tilde with respect to t. Okay, because ye just basically is a constant effectively. So when I take the derivative of it, it will just disappear. In other words, it's not dependent on t. Okay, so when I take the derivative of ye with respect to t, it will just kind of disappear. Okay, so in other words, I can now say that dy by dt is the same as dy tilde by dt. In other words, you know, that kind of makes sense because I'm considering such a small distance. Away, you know, y tilde is such a small distance that effectively it's going to be the same at kind of ye. So it's, you know, dy by dt, so the derivative of my function at y is going to be pretty much the same as the derivative of my function over that small distance. Okay, so I've got this now. We also know that what we started off with our ODE was dy by dt equals f of y. All right. Now we have just found what we've just found up here, this thing up here, that f of y, okay, f of y is equal to f dash of ye times y tilde. Okay, so are you happy then that these two things are equivalent then? So I can just say that dy by dt, which I've just shown is actually dy tilde by dt. So in other words, this is dy tilde by dt. Yeah, is equal to this right hand side here, so f dash of ye times y tilde. Okay, so what does this actually mean? Well, look, this here, the derivative of my function at a particular value, so I've actually put a value into my function, therefore I'm going to get a number out. So this thing here is just a number. Okay, this is a function. This is the derivative of my function, therefore I've linearized it. Yeah, because it's in a linear form, if you like. This is just a number. Let's call it b. Okay, so this f dash of ye is just a number. So in other words, what am I left with? I'm left with dy tilde by dt equals b times y tilde. This right hand side is just a function. Is linear, right? Because I've got a constant. This b is a constant multiplied by a function. And that function is not raised to any power other than 1. Okay, so therefore this is linear. The highest power here is 1, so therefore this is linear. So what I've done here is I've linearized it. So therefore I've got exactly what I want. So in other words, what have I done? I've changed dy by dt equals f of y, which I assumed wasn't linear, all right? And I basically turned that into this, just by considering a really, really small distance away, as y being a really, really small distance away from my equilibrium point. Okay, so for y close to my equilibrium point, this here is true. Sorry, this is kind of the simplified version, but that is the same as that. So this is my linearized version here in this box here. Okay, because that is still linearized. All right. Okay, cool. Okay. So what is the point of doing this linearization? Why do we want to do this linearization in the first place? What's the point in doing it? Well, I'm going to show you. Okay, so what did we have? I'm just going to write the linearized form down. So we had dy by dt, this linearization down. So dy by dt equals f dash of ye times y tilde. Okay, so this is our linearization. Right, now, when we get an equilibrium point, okay, so let's suppose we want to get an equilibrium point. Remember how we get an equilibrium point? We set the derivative equal to 0. So this derivative we set equal to 0, right? So in other words, we want the equilibrium point dy tilde by dt equal to 0. And that will give us our equilibrium point. Okay, that will give us an equilibrium point. right? Well, that means that if this is equal to 0, then the right-hand side, this right-hand side here, is equal to 0, right? So setting, you know, dy by dt, dy tilde by dt is equal to 0, then we're setting this right-hand side equal to 0 as well. So ye y tilde equals 0. Well, notice that y tilde, what is y tilde? Well, it's our distance, okay? It's our distance away from y, so, sorry, ye. So this is ye, this is y, you know, y tilde is our distance, okay? Therefore, y tilde cannot be equal to 0. Okay, notice these are just, you know, effectively we've got two things multiplied by each other and they're equal to 0. So therefore one of them has to be equal to 0, both of them have to be equal to 0. So y tilde cannot be equal to 0 because it's a distance. It defines a distance away, you know, a distance away from ye. You know, a distance y away from ye, or equilibrium point. So it has to be some value, because otherwise if this was equal to 0, say if this was equal to 0, then effectively, you know, ye would just be the same as y. So therefore there'd be no point of doing this whole calculation. Yeah, we've defined y tilde to be some value. You know, if we let it equal to 0, then kind of we defeat the objects. In other words, you know, ye is the same as y, so it's exactly the same point, okay, which kind of defeats the object. So therefore y tilde has to not be equal to 0. So therefore that the only other option leaves is that the other thing must be equal to 0. Because the answer is equal to 0, so therefore one of them has to be equal to 0. Y tilde can't be equal to 0, so therefore f dash ye must be equal to 0. Okay, must be equal to 0. Well, look what happens. If we set ye equal to 0, so the equilibrium point equal to 0, then this means that the derivative of 0, okay, so I've just replaced, you know, ye with 0, yeah, because that's exactly what I've done. Well, the derivative of a function which, when evaluated at 0, okay, will always be 0. Will always be 0, because look at something like this. Look at something like this. Let's say our function f of x is equal to, I don't know, well, let's change the notation just to kind of make it clear that I'm just doing an example now. So let's say we have a function, and that's, I don't know, x squared plus 4x plus 2. All right. Now, if I evaluate this function at 0, effectively all of my zeros are just, all of my x's just disappear. So this is 0 plus 2. Well, when I take the derivative of it, and this is always true, so basically anything involving you know, by putting 0 into my function, what I will get is just effectively either 0, you know, if this 2 wasn't here, I just get 0, or I would get, or I'd get a constant. Okay, so in this case we've got a constant 2. So when I take the derivative of it, well, I'm taking the derivative of a constant, right? So therefore that has to be equal to 0. So therefore, you know, this is kind of, you know, this is true in general, that the derivative of a function, which when evaluated at 0, must be 0. Must be 0. Okay? So basically, I've got exactly what I want. So basically, you know, look, I've got dy tilde by dt equals f dash of ye, which I've set to be 0. So I've set my equilibrium point to be 0 times y tilde. Okay, well, I've just shown you that, you know, f dash of 0 is 0, so this is 0 times y tilde, so 0 times 0, 0 times something must be equal to 0. So therefore I've got exactly what I want. Okay, now I'm going to look at kind of the next thing. So, you know, that's basically saying I'm putting in, you know, I'm replacing ye equal to 0. Okay, but now what I want you to do, so hopefully you're happy that, you know, if we put ye equal to 0, one of the kind of most important things for that, if we put y equal to 0 into this thing which we found, okay, f dash of ye times y tilde, if we put ye into that, then if that is, you know, if this comes out as asymptotically stable, right, we talked about what that means, so effectively it's stable, you know, for all intents and purposes, it's stable. Okay, so if this comes out as stable, then therefore the original ODE, okay, the original ODE, so for ye, so in other words, you know, ye in the original ODE is also asymptotically stable. Asymptotically stable. So hopefully you can see now that, you know, by making this linearization, we can simplify the ODE down dramatically. Okay, and we can actually gain some really important information. So if it's asymptotically stable, if we put ye equal to 0 into this thing, into this linearized version, okay, and if that comes out as asymptotically stable, then therefore that must mean that ye YE was asymptotically stable in the original ODE. And likewise, if we put YE equal to 0 into this thing and it comes out as unstable, then fairly obviously that implies that YE must have been unstable in the original ODE as well. Okay, so yeah, you know, that's kind of a fundamental part of this. So basically, if we put YE equal to 0 into this thing here, okay, and if it comes out as asymptotically stable, then therefore that must mean that YE was whatever that value was, YE, so the equilibrium point, must have been asymptotically stable in the original ODE. Okay, so the original ODE was dy by dt equals f of y. All right, and likewise, if it comes out as unstable, then therefore YE must have been unstable in the original ODE. So the equilibrium point must be unstable. So this is really useful. You know, linearisation basically is able to determine the stability of the points. Okay, and actually we can make a further generalisation, but in order to do that, we need to do sort of something a little bit further. So in other words, now what I'm going to do is, before we considered f dash of YE equal to 0, now I'm going to basically assume that it's non-zero. Okay, so therefore dy tilde by dt must also be non-zero as well, because obviously y tilde is not equal to 0. Yeah, this is what I'm considering. Dy tilde equals f dash of ye times y tilde. Okay, so this is the thing which we're considering. So therefore I'm considering this is non-zero, this is non-zero, so therefore my derivative must also be non-zero. So in other words, it must be either positive or negative. Okay, notice that y tilde is either positive or negative, right? So y tilde can either be positive or negative. So in other words, when we've got our equilibrium point, ye, y tilde can be this side, okay, or it can be this side, okay, tilde. So that basically defines the position of y. So y can be this side, or it can be this side, okay, depending on y tilde, what the value of y tilde was, okay. So let's have a look. So if y tilde is greater than 0, so in other words, y tilde is positive, what have we got? We've got this thing. So we've got ye is here, okay, and y tilde is positive, so therefore that means that y must lie over here, okay. So then what we've got left to look at is what f of ye is doing, because it's non-zero, so therefore that can either be positive or negative. So let's have a look at the case when it's positive. Well, what does that mean? It basically means that overall, because we've got f of ye being positive, so y tilde being positive, then and f dash of ye being positive, then therefore we've got a positive times a positive. You know, if you look back in this equation, we've got a positive times a positive, so therefore dy by dt, dy tilde by dt, has also got to be positive as well. So in other words, we're positive, so we're moving to the right. So we're sitting at y at the moment, okay, and therefore we're considering dy by dt being positive. So therefore we're moving to the right, so we're moving in this direction. So in other words, we're moving away from the equilibrium point. So in that case, we've got unstable. All right. Now let's consider the case when f dash of ye is less than 0. Okay, so that means then that dy by dt, dy tilde by dt, we've got a positive times a negative. So therefore, negative times a positive is the other way around. Yeah, this is negative and this is positive. Okay, so therefore this has to be less than 0. So therefore we're moving to the left. So we're at ye, remember, we're moving to the left. So therefore we're moving towards our equilibrium point. So therefore we've got an asymptotically stable equilibrium point for that case. Okay, now let's look at the case when y tilde is less than 0. Okay, so in other words, what have we got? We've got ye here and we've got y here. Okay, so we're sitting at y at the moment, and this is y tilde. Okay, so y tilde. Okay, and then let's again consider the different cases. So we've got f dash of ye, okay, being greater than 0. Well, what have we got? We've got this time, this is negative now. This is negative, and if it's greater than 0, then this is positive. So therefore, dy by dt, it's a positive times a negative, so therefore it's also going to be negative. So dy tilde by dt has got to be negative. Okay, so therefore we're sitting at y, and in this case we're moving to the left. So therefore we're moving away from the equilibrium point, so therefore we're unstable in this case. Okay, now we consider the other case like we did before. So now we consider the case when it's greater than 0. So therefore this is, when we're less than 0. Sorry, yep, less than 0. So we've got y tilde already being less than 0, and now we've got f dash of ye being less than 0 as well. So we've got negative times negative, therefore that's positive overall. So therefore dy tilde by dt has also got to be positive as well. Okay, so dy tilde, it's got to be positive. So in other words, we're sitting at y and we're moving to the right, because that's what dy tilde by dt means. We're moving to the right. So therefore we're moving towards ye, so that's asymptotically stable. Okay, so what can we say overall then? Well, when f dash of ye in both, look at what happens in both cases. When f dash of ye is greater than 0 in both cases, we get unstable. And likewise, when f dash of ye was less than 0, we get asymptotically stable in both cases, regardless of what. So in other words, we can say overall that f dash of ye, when f dash of ye was greater than 0, regardless of what the value, of y tilde was, whether it was positive or negative, we always had an unstable case. Okay, so in other words, ye was always unstable. Okay. Then when we had the case when f dash of ye was less than 0, in both cases, regardless of the value for y tilde, we had that the equilibrium point was asymptotically stable. Okay, asymptotically stable. So this is why this linearization is useful. It just basically means that this just gives us another way of solving the ODEs. We've shown how to solve an ODE using phase portraits. This is just another way which we can solve the ODE. It's just linearization. Basically, we can just look at a point which is really close to the equilibrium point and see what happens. Okay.